All right, we're back. We're still on page 134. We're just doing some problems using vectors, things that we know. This question is going to be really interesting, well, I think. We're going to try to find the area of a parallelogram which has A and B as two of its sides. So it doesn't actually really matter what A and B are, rather, as long as they are not parallel. So I'm just going to kind of draw something to say, let's say that this is A and this is B, right? So our parallelogram then is just going to be, if I duplicate this and put it here, and then if I duplicate this and put it over here. So there's our parallelogram, right? So we want the area of that. Well, the area of a parallelogram in general should be the base times the height. And that's not bad. Now what I'm going to need to find the height though, right? The base is obviously the magnitude of B. Well, obviously, I don't know. The base is the magnitude of B. So I need the height, but the height feels like something we've done before. The height, I think I can use the concept from the ambiguous case of the law of sines, right? If I put this here, then my height should just be, so let's do this. So this is going to be equal to the magnitude of B. Oh gosh, magnitude of B, and then the height, right? So the height should be the magnitude of A times the sine of the angle. That's how we've always found the height in the ambiguous case. This is no different. So it's going to be the magnitude of A times the sine of theta. All right, so far so good. Now, one issue though is theta, right? We don't exactly explicitly know how to find the sine of theta, but what we do know how to find is the cosine of theta. We know that the cosine of theta is A dot B over the magnitude of A, magnitude of B. So we can say the magnitude of, I'm going to switch them and say magnitude of A, magnitude of B, and then the sine of, okay, so that's going to be the inverse cosine of A dot B over the magnitude of A, magnitude of B. Okay, so that's because it's the angle between two vectors. The cosine of the angle between two vectors is the dot product over the product of the magnitudes. So the angle is the inverse cosine of the dot product over the product of the magnitudes. So far, I think we're okay. The next thing that I want to do, though, is I want to look at this, the sine of the inverse cosine, as one of those problems from like way back when, right? We did these types of problems. I can draw a triangle. I can use a triangle to figure out what the sine of the inverse cosine is. So what am I going to do? So I know that cosine of theta, so this, I'm going to draw a triangle. This triangle has nothing to do, it has everything to do with the parallelogram, but like nothing geometric to do with it. So I'm just going to draw a triangle here where this is theta, and I know the cosine of theta is A dot B over the magnitude of A, magnitude of B, which means in this triangle, this side is A dot B, and then this is the magnitude of A, the magnitude of B. So take a second and look at that, right? Cosine of theta is adjacent over hypotenuse, so A dot B over the magnitude of A, magnitude of B. The question now is, what is sine of that angle? Because that's what we're trying to do. We're trying to find the sine of theta. So I'm going to find that. So at this point, I have, well, I'm going to need the missing side, right? So the missing side is the square root of, this is going to take a lot of writing. I don't even know if that radical is big enough. Let me write this, magnitude of A, magnitude of B, and then I need to square that, minus A dot B squared. Okay, so I need sine of theta in this triangle. So this is going to be equal to, magnitude of A is still there, magnitude of B is still there. and then sine from the triangle is opposite over hypotenuse. Something like really nice is about to happen. So this will be, let me use blue for this. So it's the square root of the magnitude of A, magnitude of B, and then we're squaring that minus A dot B, squaring that over magnitude of A, magnitude of B. This is the discussion that caused me to think I should break this video up, because we're not even done. But look at this. So we have the magnitude of AB and the magnitude of AB. So we're like getting somewhere, right? So this whole thing is just magnitude of A, magnitude of B. Then we're going to square that minus A dot B squared. Okay. So we could probably calculate this at this point if we wanted to, because A, what are A and B? A is 512 and B is 724. So if we wanted to, we could calculate that, I think. So 512, so this will be 512 gives a magnitude of 13, 724 gives a magnitude of 25, minus, we actually did the dot product before, it was 323, right? It's 5 times 7 is 35, 12 times 24 is 288, so it's 323. So 323 squared, which is, so this is the square root of 325 squared minus 323 squared. So one thing that you can do here is that, first of all, you should have used a calculator like on this step, I think. I think that would have been a lot easier, but whatever. If you don't, this is the difference of squares. So you can make this radical 325 plus 323 times 325 minus 323, which is actually not that bad to calculate, maybe. That's 648, right? 648 times 2. So we're getting radical 1296. 1296 that's got to be a perfect square, right? That's like is that 34 squared maybe? Okay, let me switch over to the calculator and see. I think that's 36. 34, 36. Ooh, one of those, I think. All right, hold on. First thing, I'm just going to start a new document. So A is equal to 512 and B is equal to 724, right? And also I need to know square root of 1296. 36. Okay, so we got exactly 36, which is kind of neat. What I want to do though is I could have done the square root of the magnitude squared. So the norm of A times the norm of B and then squared minus the dot product of A and B squared. Okay, so this is what I would have just typed in and the calculator would spit it out. All well and good. So we can do this, and you can do this every time, and I think you should. I think it's like a really, really good exercise. But I want to do something even weirder, I think. So what I'm going to do is I'm going to create like two generic vectors. A, I'm going to say is A1, A2. And B, I'm going to say is B1, B2. And I want to calculate this thing more generally. So there's no really great reason to do this other than something amazing is going to happen. So I'm going to calculate this again, and it's going to give me an answer in terms of A1, A2, B1, and B2. So I get this. What? Okay, so that's the absolute value of A1, B2 minus A2, B1. Absolute value of, so I'm gonna write this down and then I'll switch over the notes so that you can see what I'm doing. So A is A1, A2, and B is B1, B2. Okay, switch, and then, so the area ends up the absolute value of A1, B2 minus A2, B1. All right, let's go back. And then so the amazingness of this will depend on whether or not you remember something that you may or may not remember. If I remembered to tell you to do some stuff with matrices ahead of time, you may remember this. Otherwise, you may not. This is actually the absolute value of a 2x2 determinant that is A1, A2, B1, B2. So we're taking the absolute value of a 2x2 determinant. So how crazy is this, right? So when you take a determinant, you do the diagonal, so A1, B2 minus B1, A2, and that gives you this. And it's absolute value because the area can't be negative. So what we could have done from the very start, and I'll do it like up here just to show, is we could have done the area equals the absolute value of the determinant of 5, 12, 7, 24, which is the absolute value of 5 times 24 is 120, minus 7 times 12 is 84, which is the absolute value of 36, which is 36. We could have gotten it by doing almost nothing, but if you don't see these connections, you can't do that. But this is like a really cool, very useful formula. So like you can use it to check your answers as much as you want. When I do these problems, what I like to do, so I'm basically telling you what you'll need to show, I guess, is I always start with the picture and I'll get to this point. And then from this point, I'm okay with you jumping here. And then from here, I don't know, if it's calculator, use a calculator. If it's not calculator, you know, don't, whatever. So what I'm gonna do is, this is probably a long video. I'm gonna do this problem now in basically the same way. So A is 512 and B is 724, right? So the triangle, let's say this is like A and B, and then we're told to use A minus B, B minus A. It doesn't really make a difference because the areas of the triangles will be the same. But A minus B is like this. So I knew that because I thought in my head that negative B would go over here. And so then I'd pick it up and go here, and then I'd go from here to here, and then I just drew it over here. So that's how I do that in my head. So this should be 1/2 the parallelogram. So it's going to be 1/2 of 36 in this particular case. So it's going to be 18, which kind of gets that answer really quickly. You could have done, say you hadn't done it at all. So you could go through the setup, or if you're allowed to use determinants, you could have said it was going to be 1/2 of the absolute value of 512, 724, which is 1/2 the absolute value of 36, which is 18. Or you can go through this whole process where you just use 1/2, right? So it should be 1/2 of base times height. And then everything is basically exactly the same. So this is like a really big idea. I recommend that you make up a problem or two on your own and just do it. Going through the process. So doing it this way is actually the most useful, right? Because there's a lot of key steps. There's a lot of thought that goes into it. Knowing this way is useful, but if you just use this, and I didn't tell you that you could, I'm going to ask you to prove it, and it's a nightmare. You could do it on the calculator, obviously, with no problem. And check. Always use it to check. So this is a good way to check, but not really a good way to do it because it doesn't convey a lot of like understanding to just be like, oh, it's the absolute value of the 2x2 determinant. Like what? How do you know that? So it's the process that matters. But I think that you might as well know that it is like a generalization, an awesome generalization. So I'm going to stop this here, come back in the next video, and do the next page. So I will see you there.